Welcome to this presentation. You are watching Vlsi design lecture series. And today we are going to focus on multipliers. Multiplications are expensive and slow operations. The performance of many computational problems often is dominated by the speed at which the multiplication operation can be executed. And this observation has, for instance, prompted to the integration of complete multiplication units in the state-of-art digital signal process and microprocessors. Multipliers are in effect complex adder arrays. Therefore, the majority of these adders have to be concluded, and the analysis of the multiplier gives us some further insight into how to optimize the performance of complex circuit topologies. So, and now let us discuss about the basic array multipliers. And the simple way to perform a multiplication is to use a single 2-input adder. For inputs that are m and n bits wide, the multiplication takes m cycles using n-bit adder. The shift and add algorithm that is for multiplication will add together with a bit of multiplier, which is an AND operation, and by shifting the result on the basis of the multiplier bit position. Each partial product is generated by multiplying the multiplicand with a bit of the multiplier and by shifting the result on the basis of the multiplier bit position. Now let us consider two unsigned binary numbers x and y that are m and n bits wide respectively, and to introduce the multiplication operation it is useful to express x and y in the binary representation. That is, x can be written as summation of I is equal to 0 to m minus 1 xi to power I, where y is equal to summation j is equal to 0 to n minus 1 yj to power j, with xi and yj belongs to 0, 1. And the multiplication operation is then defined as z is equal to x into y, where that is z is equal to summation of k is equal to 0 to m plus n minus 1 zk to power k. So you can write those terms as multiplied terms, that is, which will be equal to summation of I is equal to 0 to m minus 1 xi to power I into summation of j is equal to 0 to n minus 1 yj to power j, which is equal to summation of I is equal to 0 to m minus 1 summation of j is equal to 0 to n minus 1 xi yj to power I plus j. So the simplest way to perform a multiplication is to use a single 2-input adder. For inputs that are m and n bits wide, the multiplication takes m cycles using n-bit adder. And this shift and add algorithm for multiplication adds together m partial products. Each partial product is generated by multiplying the multiplicand with a bit of the multiplier, which essentially an AND operation, and by shifting the result on the basis of the multiplier's bit position. A faster way to implement multiplication is to resort to an approach similar to manually computing a multiplication. All the partial products are generated at the same time and organized in an array. A multi-operand operation is applied to compute the final product. This set of operations can be mapped directly into hardware, and the resulting structure is called array multiplier and combines the three functions called partial product generation, partial product accumulation, and final addition. So these are the three important functions that has to be carried while doing multiplication. And it is often necessary to implement multiplication of an operand by a constant. Okay, and now let us focus on partial product generation. Partial products result from the logical AND of multiplicand with the multiplier bit yj, and each row in the partial product array is either a copy of the multiplicand or row of zeros. Careful optimization of the partial product generation can lead to some substantial delay and area reduction. You can notice that in most cases the partial product array has many zero rows that have no impact on the result and thus represent a waste of effort when added. In case of a multiplier consisting of all ones, all the partial products exist, while in the case of all zeros there is none. This observation allows us to reduce the number of the generated partial products by half. Assume, for example, an 8-bit multiplier of the form, say for example 0, 1, 1, 1, 1, 1, 1, 0, which produces 6 non-zero partial product rows. One can substantially reduce the number of non-zeros by recoding this number as 2 power 7 plus 2 power 6 plus 2 power 5 plus 2 power 3 plus 2 power 2 into a different format, and you can verify the form of it is 1 0 0 0 0 1 0 with a 1 bar and shorter notation is minus 1, which represents the same number. Using this format, we have to add only two partial products, but the final adder has to be able to perform subtraction as well. So this type of transformation is called the Booth recoding, and it reduces the number of partial products to at most 1/2. It ensures for every 2 consecutive bits, and at most one bit will be 1 or minus 1. So reducing the number of partial products is equivalent to reducing the number of addition, which leads to speed up as well as an area reduction. Formally, this transformation is equivalent to formatting the multiplier word into base 4 scheme instead of the usual binary format. Therefore, y can be rewritten as y is equal to j is equal to summation j is equal to 0 to n minus 1 by 2 yj 4 power j with yj belongs to set of minus 2, minus 1, 0, 1 and 2. And you know that 1 0 1 0 1 0 represents the worst case multiplier input because it generates the most partial products 1/2. While the multiplication with the 0, 1 is equivalent to an AND operation, and multiplying with the minus 2, minus 1, 0, 1, 2 requires a combination of inversion and shift logic. The encoding can be performed on the fly and requires some simple logic gates. Having a variable size partial products array is not practical for multiplier design, and a modified Booth recoding is most often used. The multiplier is partitioned into 3-bit groups that overlap by 1 bit. Each group of 3 is recoded, and as you can see in the table, and it forms one partial product. The resulting number of the partial products equals half of the multiplier width. The input bits of the recoding process are the two current bits combined with the upper bit from the next group, moving MSB to LSB. So you can see in the table that is 0 0 0 is recorded bit as 0, and 0 0 0 1 is plus multiplicand, 0 1 0 is also plus multiplicand, 0 1 1 is plus 2 into multiplicand, 1 0 0 is minus 2 into multiplicand, and 1 0 1 is minus multiplicand, 1 1 0 is minus multiplicand, and 1 1 1 is 0 again. So in simple terms, the modified Booth recoding essentially examines the multiplier for strings of ones from MSB to LSB and replaces them with the leading 1 and minus 1 at the end of the string. For example, 0 1 1 is understood as the beginning of the string of ones and is therefore replaced by leading 1, while 1 1 0 is seen at the as the end of the string and is replaced by a minus 1 at least significant positions. So next, let us move on to partial product accumulation. After the partial products are generated, they must be summed, and this accumulation is essentially a multi-operand operation. A straightforward way to accumulate partial products is by using a number of adders that will form an array, and hence the name array multiplier. And the comparison of array multiplier, you can see that there is one-to-one topologies correspondence between this hardware structure and manual multiplication. The generation of n partial products requires n into m 2-bit AND gates, and most of the area of the multiplier is devoted to the adding of the n partial products, which requires n minus 1 m-bit orders. The shifting of the partial products for their proper alignment is performed by simple routing and doesn't require any logic. The overall structure can be easily compacted into a rectangle, resulting in a very efficient layout. Due to the array organization, determining the propagation delay of the circuit is not straightforward. You can consider this implementation, and the partial sum adders are implemented as ripple carry structures. Performance optimization requires that the critical timing path be identified first. This turns out to be non-trivial, and in fact a large number of paths are of almost identical length can be identified. Two of those are highlighted here, and you can look at those critical paths which yields the approximate expression for the propagation delay, and you can write it as T mult is equal to m minus 1 plus n minus 2 into T carry plus n minus 1 into T sum plus T and, where T carry is the propagation delay between the input and output carry, and T sum is the delay between the input carry and the sum bit of the full adder, and T and is the delay of the AND gate. Since all critical paths have the same length, speeding up just one of them, for instance by replacing one adder by a faster one such carry select adder, doesn't make much sense from the design standpoint. All critical paths have to be attacked at the same time, so it can be reduced that the minimization of T mult requires the minimization of both T carry and T sum, and in this case it could be beneficial for T carry to be equal to T sum. This contrasts with the requirements for adder cells where a minimal T carry was of prime importance. And now let us move on to the carry save multiplier or Wallace multiplier. Due to large number of almost identical critical paths, increasing the performance of the structure through transistor sizing yields marginal benefits. A more efficient realization can be obtained by noticing that the multiplication result doesn't change when the output carry bits are passed diagonally downwards instead of only to right. So we include an extra adder called vector merging adder to generate the final result that you can see in this diagram. The resulting multiplier is called carry save multiplier or Wallace multiplier because the carry bits are not immediately added but rather saved for the next stage. In the final stage, carries and sums are merged in a fast carry propagate adder stage. While this structure has a slightly increased area cost, it has the advantage that its worst case critical path is shorter and uniquely defined as T mult is equal to T n plus n minus 1 into carry into T mulch, still assuming that T add is equal to T carry. When mapping the carry save multiplier onto silicon, one has to take into account some other topological considerations. To ease the integration of multiplier into the rest of the chip, it is advisable to make the outline of the model approximately rectangular. A floor plan for the carry save multiplier that achieves this goal should be rectangular, and you can observe the regularity of the topology which makes the generation of the structure amenable to automation. Another type is tree multiplier, where the partial some adders can also be rearranged in tree-like fashion, reducing both the critical path and the number of adder cells needed. And you can consider a simple example which is shown in this diagram. And the four partial products, each of which is 4 bits wide, are shown here. The number of full adders needed for this operation can be reduced by observing that only column 3 in the array has to add 4 bits. All other columns are somewhat less complex, where the original matrix of the partial products is recognized into a tree shape is visually illustrate its varying depth. The challenge is to realize the complete matrix with the minimum depth and the minimum number of adder elements. The first type of operator that can be used to cover the array is full adder, which takes 3 inputs and the partial produces 2 outputs, the sum located in the same column and array. And for this reason the FA is called 3 to 2 compressor. It is denoted by a circle covering 3 bits. The other operator is the half adder, which takes 2 inputs in a column and produces 2 outputs. So the half adder is denoted by a circle covering 2 bits. To arrive the minimal implementation, we iteratively cover the tree with the FAs and HAs, that is full adder and half adders, starting from the densest part. And in the first step, we introduce HAs in columns 4 and 3, and this reduced tree is shown in the third diagram. So a second round of reductions creates a tree of depth 2. Only 3 FAs and 3 HAs are used for the reduction process, compared with 6 FAs and 6 HAs in the carry save multiplier. So the final stage consists of simple two input adder, for which any type of adder can be used. So this presented structure is called Vlsi multiplier, and its implementation can be done easily, and the tree multiplier realizes the substantial hardware savings for propagation delay through the tree is equal to O into log 3 by 2n, while substantially faster than the disadvantage of the being very irregular, which complicates the task of coming up the efficient layout. This irregularity is visible even in the 4-bit implementation. And there are numerous other ways to accumulate the partial products tree. A number of compression circuits have been proposed, and they are all based on the concept that when full adders are used 3:2 compressors, the number of partial products is reduced by 2/3 of multiplier stage. And one can ever go a step further and devise a 4:2 compressor, such as the Santros compressor. In fact, many of today's high performance multipliers do just that. Thank you.